Okay, so our topic to be discussed is about mathematical models and least square analysis. Mathematical models. For standard linear models, we have y is equal to mx plus b. For our standard form of the equation, we have quadratic models. We have y is equal to ax squared plus bx plus c. Exponential models are used to predict human population, animal populations, money growth, population growth, and other aspects of society that fit exponential models. This variable of an exponential model is found to be exponent of the equation. For exponential models, we have p is equal to p sub o multiplied to the quantity of 1 plus r raised to t, where p is the new value and the p sub o is our original value, and r is equal to our rate and t stands for our time. Mathematical exploration model in linear algebra. Leontief input-output model. Amount produced is equal to intermediate demand plus external demands. So we can express that as x is equal to cx plus d. And x is equal to cx plus d to x minus cx is equal to d. And d is equal to the quantity of I minus c times x. And x is equal to I minus c raised to negative 1, or the inverse of it, multiplied to d. And that is our derived equation. Suppose that an economy is divided into three sectors: manufacturing, agriculture, and services. Let x be a 3 by 1 vector called the production vector that lists the output of each sector for 1 year. At the same time, let d be a 3 by 1 vector called the demand vector that lists any external demands on the goods and services from non-productive part of the company. So we have here the inputs per unit of output. So purchase from manufacturing, agriculture, and then services. We have the manufacturing. We have 0.5, 0.2, and 0.1 for agriculture. We have 0.4, 0.3, and then 0.1 for services. 0.2, 0.1, and 0.3. Solve for the optimal production level using the internal and external demands, given that external demand is 50 units for manufacturing, 30 units for agriculture, and 20 units for services. Solution: we want to find the production level x given that the consumption matrix C and the demand vector R, where C is equal to 0.5, 0.2, 0.1, 0.4, 0.3, 0.1, 0.2, 0.1, and then 0.3. And our D is equal to 50, 30, and 20. From the derived equation, we need to solve the equation I minus c multiplied to x is equal to d by evaluating x is equal to the inverse of I minus c times d. It is impractical to actually compute the inverse, so instead we can create an augmented matrix for I minus c and use the row reduction. And for that, we have 0.5, negative 0.4, negative 0.2, and then 50, negative 0.2, 0.7, negative 0.1, and then 30. And then negative 0.1, negative 0.1, 0.7, and then 20. Using the row reduction, we came up with a result of approximately 226 for manufacturing. And then for agriculture, we have approximately 119 units. And then for services, it must produce an approximately 78 units. This will lead to balanced economy where there is no surplus or shortage. Balancing chemical equations model. Consider the chemical reaction. Nitrogen dioxide plus water yields to nitrous oxide and nitric acid. So we have nitrogen oxide and then our nitrogen dioxide plus our water, which is H2O, and yields to nitrous oxide and nitric acid. We'll label those by A, B, C, and D. The coefficients A, B, C, and D are unknown positive integers. Their action must be balanced. That is, the number of atoms of each element must the same before and after the reaction. Because the number of atoms must remain the same, we end up with the following system of equations. We have for oxygen, we have 2A plus V, B is equal to 2C plus 3D. And the nitrogen, we have A is equal to C plus D. For hydrogen, we have 2B is equal to C plus D. Rearranging this into an augmented system gives the homogeneous system 2, 1, negative 2, negative 3, 0. 1, 0, negative 1, negative 1, 0, 0, 2, negative 1, negative 1, 0. Performing the row reduction and the system gives, so using the row reduction, we have 2, 1, negative 2, negative 3, 0, 1, 0, negative 1, negative 1, 0, and 0, 2, negative 1, negative 1, 0, 2, 1, 0, negative 1, negative 1, 0, 0, 1, 0, negative 1, 0, 0, 2, negative 1, negative 1, 0, into 1, 0, negative 1, negative 1, 0, 1, 1, 0, negative 1, 0, so 0, negative 1, negative 1, 0. And for our final matrix, we have 1, 0, 0, negative 2, 0, 0, 1, 0, negative 1, 0, 0, 0, 1, negative 1. Okay, so we have A is equal to 2D, and B is equal to D, and C is equal to D. That is using our row reduction. In this chemical equation, we see that D, the coefficient of nitric acid, is a free variable. Mathematically, this means that we can freely choose D to any value we like, but scientifically, we choose the smallest positive integer, which is 1. Hence, A is equal to 2, and B is equal to 1, C is equal to 1, and D is equal to 1. So the balance equation becomes 2 nitrogen dioxide plus 1 molecule of water yields to HNO2 plus HNO3. Next is our least squares analysis. Least squares. We recall that an m by n linear system AX is equal to B is inconsistent if it has no solution. Equivalently, AX is equal to B is inconsistent if and only if B belongs to the column space of A. Inconsistent systems do indeed arise in many situations, and we must determine how to deal with them. Our approach is to change the problem so that we do not require the matrix equation AX equal to B to be satisfied. Okay, for our example, the following data show atmospheric pollutants Y relative to the EPA standard at half-hour interval T sub I. Here's our table, our data for T sub I and Y sub I. For T sub I1, we have Y sub I of negative 0.15. For 1.5, we have 0.24. For 2 of T sub I, or our half-hour interval, we have Y sub I, we have 0.68. And for 2.5, we have 1.04. For 3 of our half-hour interval, T sub I, we have Y sub I, or atmospheric pollutant, of 1.21, 3.5 to 1.15, 4 to 0.86, and 4.5 to 0.41, and then 5 of T sub I, we have negative 0.8 of Y sub I. A plot of these data points, as shown in the figure previously, suggests that a quadratic polynomial y of t is equal to x sub 1 plus x sub 2t plus x sub 3t squared may produce a good model for this data with f sub 1 of t is equal to 1, f sub 2t is equal to t, and f sub 3 is equal to t squared gives a matrix of A, which is equal to 1, 1, 1, 1, 1.5, 2.5, 1, 2, 4, 1, 2.5, 6.5, 6.25, 1, 3, 9, 1, 3.5, 12.25, 1, 4, 16, 1, 4.5, 20.25, 1, 5, 25. And for our vector x, we have x sub 1, x sub 2, x sub 3. And for our b, we have negative 0.15, 0.24, 0.68, 1.04, 1.21, 1.15, 0.86, 0.41, and negative 0.8. The rank of A is 3, and the normal system is 9, 27, 96, 27, 96, 378, 96, 378, 15 or 1583.25, x sub 1, x sub 2, x sub 3 is equal to 5.36, 16.71, and 54.65. Okay, so applying the Gaussian elimination, we arrive at negative 1.9317, 2.0067, and negative 0.3274. So we obtain a quadratic polynomial model of y of t is equal to negative 1.9317 plus 2.0067 t minus 0.327 t squared. Okay, so we have least squares analysis in statistics. Given below are data relating to the production of sugarcane industry. Fit a straight line trend by a method of least squares and tabulate the trend values. Okay, for year 2000, 2001, 2002, 2003, 2004, and 2005, and 2006. So here are the production of sugarcane. We have 40, 45, 46, 42, 47, 50, and 46 respectively. Solution, computation of trend values by the method of least squares for years. We have for the year 2000 to 2006, we have n is equal to 7. And then the production of sugarcane, the summation of y, we have 316. And for our summation of x, we have x minus 2003, we have negative 3, negative 2, negative 1, 0, 1, 2, 3. And for our x squared, we have 9410149, or summation of our x squared is equal to 28. And for our xy, we have negative 120, negative 90, negative 46, 0, 47, 100, 138. For our summation of xy, we have 29. Trend values are our yt. We have 42.04, 43.07, 44.11, 45.14, 46.18, 47.22, 48.25. For our summation of yt, we have 316. A is equal to summation of y over n is equal to 316 over 7 is equal to 45.143. For our b, we have summation of xy over summation of x squared. We have 29 over 28 is equal to 1.036. Therefore, the required equation of the straight line trend is given by y is equal to a plus bx. And for our y is equal to 45.143 plus 1.036 x minus 2003. The trend values can be obtained by when x is equal to 2000, yt is equal to 45.143 plus 1.036 times the quantity of 2000 minus 2003, which is equal to 42.035. When x is equal to 2001, yt is equal to 45.143 plus 1 0.036 multiplied to the quantity of 2001 minus 2003, we have 43.071. And similarly, other values can be obtained through this equation or through this process. Research on partially scarce method based on deep confidence network in traditional Chinese medicine. Authors Wang Pingxiong, Xiangsi Li, Qingxia Zheng, Xiang Qiangdu, Binet Qingqing Chen, and Shen Zhu. For the abstract, partially scarce method has many advantages in multivariate linear regression modeling, but its internal crossing checking method will lead to a short reduction of the principal components about Chinese medicine data is particularly sensitive. This paper proposes a kind of partially scarce method based on deep belief nets. This method mainly uses the deep learning model to extract the upper level features into the partially scarce model for multiple regression and evading problem that selects the number of principal components, continuously adjusting the model parameter until satisfied while please accuracy